Hi everybody, I am Andrés Tassara. I am the Deputy Director of CICLO and the Principal Investigator of Research Line R2. And I would like to present you a summary of the activities that we have been doing over the last 3 years, analyzing the spatial dimension of the seismic cycle and what we are starting to do in the second phase of CICLO, developing mechanical numerical modeling of the seismic cycle. So let's start just by establishing that during the first 3 years of CICLO, in this research line, we aim to characterize the spatially variable frictional structure of the Chilean megatrust in order to establish a segmentation model of the margin. And in the literature, there has been used different proxies, independent proxies that have been commonly used in isolation in order to understand the frictional, the variable or patchy frictional structure of a megatrust. These independent proxies cover a range of time scales. And we have been working with these different proxies, and actually for most of them we have produced our own results. And I would like to draw to your attention to the talks of Martinez that has been working in collaboration with Research Line 3 in terms of coastal geomorphology, and also Catalina Santelices, currently working with the V-value and based on seismicity, spatial temporal analysis of seismicity in collaboration with Research Line 5. And you can see some examples of what we are doing developing these proxies. But what is important to this research, or to this summary, is the work done by Diego Molina in the first part of his PhD thesis, analyzing or trying to analyze the spatial correlation between these three different proxies by means of the principal component analysis. And from this integrated analysis, we can compare the result of this analysis with the instrumental and historical earthquake rapture that has been produced in Research Line 1, and the geological structure of both plates, in order to create a segmentation model and to investigate the physical nature of asperities and barriers. And this is what we already did, and a paper in JGR has been recently published with Diego as a first author. This, as I told you, this is the first part of Diego's PhD thesis. And I will just show you a couple of slices in relating or explaining what we did in this paper. So we created these different proxies from the data. So in the paper we explained how we create the gravity anomaly, geodetic locking, and friction from the Coulomb, critical Coulomb wedge theory. But what is important is not the particular spatial distribution of these proxies, but the correlation between them in space. And we developed, or Diego developed, a tool based on the principal component analysis that allow us to extract the skeletal features of these correlated fields. And from this we take the trench normal principal components of the three fields that you can see here, from in green from basal friction, red for locking, and blue for gravity, noting that they are pretty much correlated between them, and also with the distribution of seismicity and the slip from different earthquakes that we have in the catalog. And this is an indication to us that we are mapping actually with the PC, with the principal components, the up dip and down dip limit of the seismogenic zone. And we identified that inside this zone we are in a velocity weakening regime, thinking on the rate and state friction theory for faults. We can also extract the a long trench empirical orthogonal function that are similar to the trench normal principal component, and this is shown here from north to south, for the three different proxies correlated also with the seismic parameters. And we can see that these are nicely correlated also, or they have some correlation, I would say, from north to south, and particular for the changes in gravity, and based on the theory that we developed in the paper also, we can identify, or we can hypothesize that these the regions that are related with positive magnitude of the gravity EOF are unstable velocity weakening zones inside the seismogenic zone, and negative values of gravity are related with conditional stable regions. And from the changes in gravity, from the changes in polarity between positive and negative, we can see here that we define actually the limits of unitary segments. We compare these unitary segments and also the reconstructed proxies for the first principal component analysis mode of the three different proxies. No, here is gravity, friction, locking and friction. We compare the reconstructed distribution of these proxies with our seismic or our segment boundaries or our segmentation, and we compare that with the earthquake raptors and seismic barriers extracted from Reasearch Line 1 and the work of Filibosyan and Meltzneff, recent work of 2020. And from the integration of these different results, as we can see here, we create this formal seismic segmentation model for the Andean margin, which is a very important result of our research line and allow us to move toward a more model-oriented research. And that is what we are actually doing, or would like to do during the second phase of Ciclo, to move from an observational analysis to a more object-oriented modeling of the seismic cycle. We are doing this stretching our collaboration with the Anillo Precursor project, which is led by Marcos Moreno. Marcos is leading also Research Line 5 of Ciclo, and we are working very nicely together in order to add more synergies to the numerical modeling approaches that we are using. And one of the first things that we are doing is actually to use the inspiration that we have from the results that I showed you previously, in order to set some numerical modeling efforts that we have. Particularly, it is interesting to us to analyze the role that probably these seismic barriers could have in terms of patterns of earthquake in time. Normally, barriers in a megatrust has been modeled as velocity strengthening zones, but we think that these are better described as conditional stable velocity weakening zones inside an unstable sliding velocity weakening zone, rounded by rate strengthening or velocity strengthening regions. With this is very new. This is something that we are proposing and testing through numerical modeling in the second part of Diego Molina's PhD talk, PhD research, and you can see the video that Diego produced for us for this annual meeting, showing and explaining these nice results. He's working with Jean-Paul Ampuero, using CUDIN, a quasi-dynamic earthquake raptor modeling that allow us to study the evolution of seismic slip and also locking in time at scales of 1,000 years, showing that these conditional stable barriers have a rich range of different seismic behaviors. We are also working in getting the two-dimensional terminal structure of the Andean margin, and a paper is in preparation showing an analytical model that we are doing. Íñigo Echeverría also has a video that can show you what we are doing in terms of this research. And one of the main objectives also of our research line during this second phase is to generate finite element modeling to be compared with this analytical model in order to have a better constrained three-dimensional thermal structure of the Andean margin, which is quite important in terms of the seismic cycle, because as we know, the thermal structure dominates the rheology of the lithosphere and can be very important in the viscoelastic relaxation, as Carlos Peña demonstrated in a recent paper where we participated also in EPSL in 2020, showing how this temperature-dependent rheology is fundamental in order to explain the post-seismic relaxation after the Maule earthquake. And this is also something that we can incorporate into the more sophisticated numerical modeling of the seismic cycle at the scale of 1,000 years. As you can see here, this is part of the PhD thesis of Joaquin Julve. You can see a video of Joaquin showing the preliminary results that he created in collaboration with Sylvain Barbot. We are using Sylvain's codes with, in this case, a very rough representation of the temperature field in the viscous part of the lithosphere, the rest of the elastic part, and we have a return state friction fault here, and we can see how nicely time evolution of slip is created in this kind of simulations between a velocity weakening and velocity strengthening zone. And as we can see here also, Joaquin showed us in his video that the use of a viscous viscoelastic or thermally dependent viscoelastic response of the lithosphere create a quite different cumulative slip pattern in time compared with the elastic case, and that is quite important and very important, and we are investigating this way. So what we want to really do during the coming 2 years is to go from 2D to 3D models of thermally dependent rheology, incorporated dynamic square rupture of rate and state megatrust, and that is where we want to go with the research in this research line. So thank you very much.